Welcome everyone. My name is Hannah Drake, and today I'm going to be presenting a proposed experimental assessment of gear location marking strategies for high-density fisheries. As this work is still preliminary, we ask that you please do not share on social media. As many of you know, gear set in a traditional fixed gear fishery is comprised of some number of traps which are set on the seafloor. At the terminal ends of the trawl are end lines which are connected to the surface using buoys. These surface buoys act as markers and let a fish harvester know the approximate location of gear set on the seafloor. When fishing with on-demand gear, the surface buoys are removed, meaning there is no longer a marker at the surface. Without this marker, fishermen trying to lay their gear or the mobile fleet trying to navigate a field of fixed gear is at a much greater risk of gear conflict. And it's this gear conflict which is considered one of the greatest challenges to the development of on-demand gear. So I will briefly clarify some terminology. Gear localization is simply the process of positioning gear on the seafloor. There are many ways of doing this with varying levels of time and effort. Gear location marking, however, is the ability of a harvester to locate on-demand gear in such a way that minimizes impact to a given fishing operation, and for that location to be easily communicated to other fish harvesters and enforcement. For assessing accuracy, gear localization is still a useful tool for validating on-bottom position, and I'll touch on this a bit more later. There are three strategies of gear localization that are relevant to this presentation. The first strategy is GPS marking. So as the gear is set, the position of the deployment is captured on the software and then uploaded to some form of cloud interface. Many commercially available on-demand systems use this method, as a GPS is the only thing required to mark the position of the gear. So the second method is ranging. When the gear is on bottom, the slant range to the gear is calculated as a product of speed of sound and one-way travel time. And by measuring water depth, we can calculate for surface distance or surface range. So this might be familiar to you, and that's because this is Pythagorean theorem. I managed to sneak some math into this presentation. So by knowing A and C, we can calculate for B. So having calculated surface distance, we know that the gear is somewhere on the perimeter of this circle, but it's not clear where. By doing a survey of ranges around the deployed unit, considered good geometry, we can identify the intersection of these circles and calculate the true on-bottom position of the gear. The last strategy I'm going to talk about is directional ranging. These systems also calculate slant range to the on-demand unit, but because the transducer is comprised of an array of hydrophones, the difference in time that each hydrophone receives sound allows the system to calculate bearing to the unit. This allows the topside system to position the gear with one signal. So the key difference between these systems is the level of accuracy they provide. GPS marking doesn't capture where gear ends up on the seafloor. In a fishery where people are not setting near one another, GPS marking may be a good option since the technology is widespread and affordable. But as demonstrated by the picture on the left, many fisheries are operating at a high density where fishermen are setting as little as 8 meters from one another or themselves. In these instances, GPS marking may not be suitable. Considering that each fishery may require a different degree of accuracy, how can we assess the suitability of these technologies relative to the needs of harvesters? It was this question that got our team involved in testing gear location marking options. The Canadian Wildlife Federation team has been trialing on-demand gear for 6 years with a focus on empirical data collection and harvester engagement. As many of the fisheries in Atlantic Canada would be considered high density, we've begun trialing emerging gear location marking options and developing methods to test their accuracy. Currently, commercially available gear location marking options use either GPS marking or a directional ranging system. For GPS marking apps, our methods want to assess the accuracy of the deployment waypoint and how different that position is from where gear settles on bottom. For directional ranging systems, we want to know how accurate the reported on-bottom position is relative to the gear's true position. And while there are currently no commercial options that use ranging for gear location marking, the ranging ability of most on-demand systems can be used to calculate the true on-bottom position of gear. By calculating that position, we can find where gear is landing on bottom and validate the on-bottom position reported by the directional ranging systems. As for our proposed methods, a GPS marking software could be assessed as follows. A trawl is deployed in realistic fishing conditions with an on-demand unit attached. The deployment location, or the place where the on-demand unit hits the surface, is marked on the system software and a handheld GPS at the same time and place. An acoustic survey, or ranging survey, is then performed to determine the on-bottom position of the gear. And this assessment of the software might qualify how easy it is to use and assess the accuracy of the deployment location relative to where it drifts to. For a directional ranging system, a trawl is deployed in realistic fishing conditions with an on-demand unit attached and the deployment location recorded. These systems will report on-bottom position. An acoustic survey would then be performed to compute true on-bottom position so that these waypoints can be compared. Because reported on-bottom position is sensitive to any inaccuracies in bearing, you would want to record reported position at various distances from the unit to capture bearing inaccuracy. Again, suitability may be qualified based on the ease of use and the system's ability to release the unit. The accuracy of the on-bottom position would be calculated and any potential sources of error would be assessed. CWF has been conducting trials using these methods over the past 2 summers, and I will quickly present to you a few of our preliminary results. For GPS marking, we have conducted a few trials using EdgeTech's Trap Tracker. Of the directional ranging systems, we have tested 2 gear location marking systems, Teledyne Benthos' Trackit and Roplus Systems single ping positioning. Here are just a few visual references from our trials. On the left is a pole mount that we use to trial the directional ranging systems. When in use, the pole is swung perpendicular to the water so that the transducer is below the hull. And while these systems may be best trialed with through-hull transducers, the pole mount has allowed us to more easily trial the gear on different vessels. On the right is an EdgeTech attached to a riser MTA. We used EdgeTech's ranging function to perform our acoustic surveys and calculate on-bottom position, which was then compared to the on-bottom position reported by Roplus Systems. This is a summary of the testing we've performed. So far, we've done 8 drift tests using EdgeTech. We've also done a number of accuracy tests on both the directional ranging systems. I haven't yet finished the analysis of the directional ranging systems, so for now I'll just show you some preliminary results from our drift tests. This figure shows the results of 8 deployments, each dot representing deployment, and shows the distance difference between the deployment location captured by Trap Tracker and recorded on a handheld GPS. Tests were conducted in 4 different areas as represented by the color of the dot. Median distance difference was 21 meters with one exceptionally large difference of 96 meters. In this figure, we see the approximate drift distance of the unit from where the GPS recorded deployment to where the gear was positioned on bottom by an acoustic ranging survey. Drift distance is plotted on the Y with depth plotted on the X. Each location is marked by a different color. While the sample size is small and we have yet to model other factors such as current, set direction, and tide, these results suggest what we already suspected, which is that drift distance is impacted by water depth. This concludes my presentation. I'd like to thank the CWF Marine team and all the fish harvesters who have helped make this work possible. I'd also like to thank our funders for their support. Thank you for your time, and I look forward to hearing your feedback and questions.